let us start where we left off, okay? Because this is important, we will use it only because mathematical notation sort of writing everything in sentences is difficult and you want to be exactly precise. So, some notations come in, okay, if we interpret it in an unambiguous way. So, as we said, this means this is basically a common math notation if you have not seen before. Box n means the first n numbers, n natural numbers. Again, you assume, let us say, this is not necessary. You can have games where action space is also infinite, but for our purpose, let us say, we will assume that the actions of the types of games we are analyzing, they will have a finite number of actions. Okay. Action space is again a direct product of the actions available to each individual player. Payoff, I had a very interesting conversation regarding what a payoff actually represents. So, let me just, so payoff, sometimes utility function, these are the various names that are used. That basically just tells you that given that the n players are playing this strategy or taking this course of action that describes a tuple, right, n size tuple, what is the payoff or what is the utility for this thing for the individual I, for the player I. Okay? That is what this payoff function is. Okay. I will come to that mixed strategy in a minute, we will get into it in details. So, a game is, so the type of game that we are talking about, they are called normal form games. Okay. That is entirely specified by these three things: the number of players, the actions of the number of players also sort of tells you the identity of the players. Okay. So, n here when I say 1, 2, 3, 4 all the way to n, it is basically you are assigning an identity or a name to the players. Okay. And you have the possibility of the all possible actions available to them and what is the payoff. Okay. So, now there can, I will just briefly state that there are games where there would be more. So, for example, the utility here, see the utility function here, this is defined purely on the direct product of the action spaces for individual players, right. So, in other words, if suppose we are playing rock, paper, scissors, if I play rock, you play paper, whatever my utility will be in step 1 will be the same as suppose after 10 rounds, will remain the same after let us say 1000 rounds and so on. There are games where this is not the case, where basically the sequence of events that happen leading up to this this thing has an effect on the payoff. Okay. Basically, these are called games with history. Those are called extensive form games, and we are not going to sort of visit them in details in this part of this, at least I am not going to, maybe one of the other speakers can. Okay. All right. Now, mixed strategy. So, an action is a pure strategy. If I choose to play rock, it means I am playing rock with probability 1, versus I could have a randomized strategy, where I say I am going to play rock with probability 1/3 and paper with probability 2/3 and I am never going to play scissor, right. But I will play, it means playing scissor is with probability 0. Okay. So, that kind of a thing is what is called a mixed strategy. A randomized strategy is a mixed strategy. That randomized strategy is defined over the possible actions available to me. So, a mixed strategy is equivalently defined as a distribution over the action space of the player. Okay? All right. Okay. So, given a normal form game of this kind, we will, so let me just go a little bit into this notation. It matters. If you get lost, ask. Okay? Everybody takes a bit of time to sort of get used to it. Once you do, it is not very complicated. So, the set of mixed strategies, MS's mixed strategies available to player P are all distributions over his action space. Okay. Distributions are what? You can think of a distribution as a vector of possibilities where the coordinates are all between values 0 and 1 and they all add up to 1. So, it is a stochastic vector. It describes a probabilistic event. Okay? That is what I mean by a distribution, and it will be denoted like this. Okay? So, this is a vector of possibilities. What is the size of the vector? It basically the size is equal to the number of actions available to player P, right. So, size of this set SP, there should be a cardinality sign here, sorry, and the summation of the coordinates is equal to 1. So, this notation should be seen as XP denotes the mixed strategy of player P. XP evaluated on the small SP tells me what is the probability that player P plays strategy, plays action SP. Okay? And all of these possibilities should add up to 1. This is what is a distribution. Okay? So, for the example, take a toy example, rock, paper, scissor. There are 3 actions available to anybody. So, this summation would be over 3 actions, rock or paper or scissor. XP for every individual player would be XP of rock. What would be the XP of scissor? XP of paper, right. That would specify the mixed strategy used by player P to play in rock, paper, scissors. Now, you can, as you vary the values of these things, you get different strategies. Okay? So, a pure strategy or an action is a type of distribution where only one of these coordinates is 1 and everything else is 0. Correct? Okay. Now, so an element of this basically where people are playing an element of S is basically this curly S is specifies the actions taken by actions. I am making a distinction between saying actions versus strategies. Okay? Actions are individual, like just playing rock or just playing paper, and so they are known as pure strategy. Usually the term in the book textbooks is pure strategy profile, but it might be visually easier, convenient for you to think of it as a vector. Okay? So, similarly, a direct product over this is a set of mixed strategies for player P, direct product of this space for each of across all the individual players is called a mixed strategy profile. So, this basically, if you list out all the possibilities here, it will tell you all possible mixed strategies that each of the players can play at any time, right, all of them, all possibilities. When we think about players playing randomized strategies, it is usually assumed that they are choosing their strategy independent of other people. Okay? Now, this might be because you do not believe that there is you do not necessarily know what they will do, right. So, you basically are to yourself, you are just arguing for what is good for you and so on, trying to reason about it and so on. So, that is one way of thinking of independent, like I can't coordinate with this person, that person is acting in selfish way, I am acting in sort of way, and so basically our strategies are not sort of correlated. Okay? All right. So, now notice one thing. So, just pay attention, if you understand this thing. Okay? This is a function that is described as part of the game. This is a utility function of our player, specifying the utility of each player P based on the actions of everybody including himself, right. When people play mixed strategies, the utility they gain from them playing mixed strategies and potentially other people playing mixed strategies cannot be directly inferred from utility function by just reading off. Then we talk about expected payoff. Okay? Expected payoff means on an average, given that we are playing this is the mixed strategy profile, what is the expected payoff for each individual player? Okay? So, that is what, can you guys, okay, yeah, this is the gallery thing. So, So, the expected payoff for player P is this is the notation it is used. It is easier to use this in equations and so on, but do not confuse UP with this. Okay. Over here the input taken here is a vector of actions, here it is a vector of mixed strategies. Okay. So, and what you get out of is basically a simple expectation expression. You are summing over all possible action space, all possible action profiles. You are saying you know this is the payoff for player P for action profile S. S is a vector of actions that each of the individuals take, this small s, and probability that this pure strategy, this S, the small s is a vector of strategies, right, that they are actually, the players are actually playing this. What is the probability that the individual players are actually playing these strategies or using these actions? That is this expression, probability that pure strategy S is sampled. Yes, maybe write down.
Isn't there a probability associated with it?
X is a distribution, X is more than a distribution, X is a vector of distributions. Let me write it here. Where do I write? This side or board? That this is okay? I am a bit sensitive to chalk, that is all. So, small s, this small s, think of it as, if it helps you think of it as, I did not want to overload the slide, so I did not have this bar notation and all. This is set of, let us think of it as A and AI is an action from the, is this okay? X on the other hand is of this kind. Each xi is distribution. Let me write it in long form. Is there an eraser here? Let us say where, okay, xij, okay, summation of I do not want to change the notation, xi1, xi2, xi, sorry, I am just trying to keep as consistent without xi, whatever, m maybe. One, and this is for all I in N. So, this is the set of all possible action profiles. This is a set of all possible distribution profiles, also called mixed strategy profiles. Each of this is a stochastic vector of this kind. Okay. Why we call it stochastic vector? Basically, this represents a probability distribution. Each of these values tell me what is the probability that individual player I plays action A1, probability that player I plays action A2, and so on and so forth. Therefore, it adds up to 1.
So, m is equal to size of SI.
Yes, yes, that's what exactly. Okay.
Set of all action profile is biggest, right?
Biggest matlab this is
The S bar should be S biggest, right?
no, S bar is in an element of, okay, you are right.
That should be
This you are right, sorry. Okay. This is basically written differently. It is basically individual action space. Is this okay? Yes, thank you. Each this small s that I was writing is a vector that looks like this. Okay. So, now when I say given a mixed strategy profile x, let us call, sorry, this is not, let us call it, what am I calling it, delta, sorry, okay, delta, x in delta, I know x looks like this. I want to compute payoff for player P, okay, for P when all the players are employing this strategy, right. This is basically, if I think of x, x is a vector of this kind, x1, x2, x3, xn. See if you can visualize this. x1 tells me, suppose they are all, suppose they have the exact same action space, okay, they like rock, paper, scissors, just for simplicity. It does not have to be that way, but for simplicity let us call it this. So, x1 is an m length vector, let us say each of the SIs are actually of size m, okay. So, this, let me take a smaller vector, maybe 3 of this thing, okay, x3, this is like comma. So, x11, x21 and so on and so forth. Okay. So, if x is the strategy that they are playing, x consists of looking at these values, these are probability, I think they are called density functions, I forget what the precise name is, probability mass. So, x11 this coordinate, x21 this coordinate, they are basically telling me what is the probability that player 1 plays action 1 under x, player 2 plays action 1 under 2 under x and so on. Okay. So, this is why if I were to compute the payoff for this player P, I am basically my sample space. If you understand expectation, the sample space basically consists of all possible tuple of actions or rather action vectors. Okay. So, that is why we get this notation, this is the curly s. Probability that S is being played, or in that case I have written sampled, okay, and times what is the utility that the player P derives from this event, that S is being played, right. S is being played, utility this times this. Okay. Now, the fact that, let me write this here, this is all this says. I am thinking of the entire probabilistic experiment as being broken into all these possibilities. This action profile happens, or this action profile happens, or this happens, or this happens, and this happens. And I have computed the probability value associated with each of those events. And then I am doing the I am just simply applying the expectation calculation. Okay. Now, so remember I said that when we talk about randomized strategies, we assume that every individual is playing independently. Okay. That allows us to simplify this expression. When I say probability S is being played, this is a vector, right. So, this basically becomes this expression, product that probability player I is playing small si, or rather over here as I have said AI. action AI. Okay? I can write here. SI is better, right? Yeah. I had changed this notation to AI when I was teaching the course because of the small and capital and lowercase this thing. Ting PI is not I is playing SI. Okay. Do I know how to compute this value? Probability I is playing SI. It comes from where? Correct. Because this whole thing is with respect to x, right? The distribution vector, the vector of distributions x. So, x tells me that under x, what is the probability that this individual I is playing the strategy SI, and where will I get this value? Basically, the SIth coordinate of xi. Okay, that's it. Okay. This is what we mean by this.
The utilities need to modify.
Yes, sorry. Yes. Yes, sorry. Okay. All right. So, okay. So, this is the expanded. I already wrote it here, so you can just see it's the same thing. I do make calculation mistake, but this is not calculation, this is concept, it's applying definition. Okay. All right. So, now there were a lot of questions on, I kept it vague, I described Nash equilibria more sort of in terms of pure strategies. What does Nash equilibria mean, or does it mean anything when players are allowed to play randomized strategies, right? So, for example, if you go back to the rock paper scissors example, we saw that there are no pure strategy Nash equilibria, meaning for any possibilities that you and I play, there is always something one of us can do to get a strictly better payoff, right. So, rock and paper, well, rock and paper bad example, rock and scissor, let us say. So, actually rock and scissor, so rock is beating scissor, the person who is playing scissor realizes if I switch to paper, I will win, right. It is a unilateral strategy, because the other person is still continuing to play rock, he is not changing. That is a very important part about Nash equilibria that I need you to keep in mind. It is a unilateral strategy, only one person changes, everybody else remains the same. Okay. So, rock paper scissors does not have a pure strategy Nash equilibria. The question is, if people are playing randomized strategies, right, the kind that we ask, I am going to play 1/3 with probability 1/3 I will play rock, with probability 1/3 I will play scissor, right, and the other thing would be also with probability 1/3. Then can we still talk about Nash equilibria? The point is, the definition can still be reworked, except that now you talk about deviation strategies that allow mixed strategies. You say that no individual has a unilateral deviation strategy, right, that might be randomized, right, because just because there is no deterministic strategy that gives him a strictly better outcome does not necessarily mean that there may not be a mixed strategy, right. If such a thing is true, then that needs a proof. So, we extend the notion of Nash equilibria all the way to incorporate mixed strategies in this way. The idea is, we say X mixed strategy profile is a Nash equilibria if there does not exist any player who deviates, instead of, let us say there does not exist an xi who changes to, let us say, an x prime I, a different mixed strategy, and gets, and everybody else remains the same, they are still playing whatever they were playing in under x, and he gets a strictly better outcome. And here the better outcome is in terms of expected payoff. Okay. So, the deterministic definition and ideas can be extended to the randomized setting in an analogous way. Okay? So, these are our definitions. Now, the question is, what do these definitions, do they give us anything valuable? Right? As a math student or a scientist in math aligned field, we are free to define whatever definition we want. Question is, why should anybody else care? It turned out this definition of Nash equilibria has been so influential. It really moved not one subject, multiple subjects. This definition alone, as simple as this might seem, and we will see a proof that was given to show that such a thing always exists in finite games, really was a game changer. Okay? No, okay, these are different properties. This is, I think I switched a little earlier. So, I just wanted to say that there is a notion of Nash equilibria. I did not write the definition, but I explained to you in words what it would mean for a Nash deviation to exist or not exist even in the presence of randomized strategies. Okay? All right. So, let us think. So, the definition of Nash equilibria is, this was supposed to not come right now, this we were supposed to sort of just focus on this, sorry. So, this is the definition of Nash equilibria as it was given and as I was saying. A distribution profile, a mixed strategy profile is a Nash equilibria if and only if for all players P and mixed strategies x prime P, player P's deviation is x prime P, the expected payoff of P from x is at least as much as his payoff from playing that new strategy, and while others remain the same. Okay? So, this is the definition of Nash equilibria as we just now discussed. Is it okay? You are able to comprehend what this means, right? Okay. Now, this is equivalent to this definition, which is that if for all players P, X is a Nash equilibria if and only if for all players P and actions, see, instead of talking about mixed strategies, we have now reduced the Nash equilibria condition to testing something about the actions only. We are talking about any two actions available to player P such that in this particular strategy, in this particular mixed strategy profile, player P plays the action SP with non-zero probability. Some of you who are familiar with stochastic terminology, this means the SP is in the support of the vector XP, okay? But just means that player P plays action SP with non-zero probability, okay? Then we have this case that player P's gain, expected gain from playing this strategy SP, which gives him which is basically non-zero probability of playing this thing, while others remain the same, is at least as much as any other action that there might be. So, I'm going to let you read this for a minute, just read it for a few seconds, then I'll try to draw your attention to the thing that is important here. Are you able to follow what the statement is?
Here for the player P, you're just replacing SP with S prime P with the same problem.
No, you're talking about this definition. Sorry? So, yeah, so here, so this is the canonical definition of Nash equilibria, right? Here we are talking about the two actions. We are basically saying an action in X, this when player P is actually playing the mixed strategy XP, SP is an action which he is playing with non-zero probability. That will give him at least as much payoff as if he were to play any other strategy, any other action. This S prime P may or may not be of value greater than 0 in this mixed strategy for player P.
I think the confusion is about this new notation in PS. So one player is playing the pure strategy, the other player is
Yes, yes, yes. Okay, sorry. This was there, okay, I'm sorry. This is true. This basically means, yes, you have basically untoggled the XP this thing. You are saying all the old players other than P are all playing the same strategy that they were using in X, and this player P has switched to a pure strategy or an action SP. Okay, similarly you interpret this. Sorry, I didn't, okay. So, all actions that have a non-zero probability of being played under X will give this player the same payoff, because S prime and SP, they are symmetric in the sense that if they are both non-zero, right, if they both are this thing, then you change this quantities should remain the same. Okay, that is probably too confusing. What I am trying to say is, you lose the player basically gains nothing. He was playing the mixed strategy XP, okay. Then he sees, oh, these are the actions where which I am actually have a 0 I have not all those actions where the value is 0 basically means he is not playing this. If in the rock paper scissor game, always go back to that just to think about it. If I were a player who always will play either rock or paper and never play scissor, then this condition would be only applicable to rock and paper, okay. So, that condition says, now let me think, am I missing out something? If X is a Nash equilibria, by the fact that I am not playing that third strategy which was scissor, right, I am not actually losing out on a utility value, because playing that strategy, if I were to shift to the scissor, cannot exceed if I completely ignore rock the mixed strategy and just continue to play rock. Okay. Take an example where I am a player who is playing, let us say, only rock and paper. I am not playing scissor, okay. And here among the two of us, we have reached a Nash equilibria somehow, okay. We are saying, you know that this, we have not reached, you know that the strategy we are playing, you are playing a mixed strategy, I am playing a mixed strategy. This constitutes a Nash equilibria if the following condition were true, that I am a deviating player, I will change my strategy, okay. Instead of playing rock and paper 1/3 and 2/3 of the times, okay, I am now going to say, no, I am going to actually play the scissor. My utility, if X is actually a Nash equilibria, then my utility cannot increase by me just merely shifting to scissor. Why does that make sense?
Following some other
correct, that is the definition of Nash equilibria, that there is no other deviating strategy, right. There is nothing I individually can do to increase my payoff. That should also include pure strategies. There is no mixed strategy. Mixed strategies are a more generalized notion of pure strategies, right. Pure strategies are single action. If there are no strategy, using this definition, mixed strategy that will give me a strictly better outcome, there should also there should not be any single action I can employ that will give me a strictly better outcome.
That would be saying the single strategy cannot be better than the mixed one, but here you are comparing two different pure strategies.
Yes, that is fine, but I am just saying, just using X to say that I am saying that right now I am not actually gaining anything. Suppose over here it was not SP, it was just X. I am just trying to draw why this sort of a definition makes sense. So, from X I realize just switching to a pure strategy, if X is a Nash equilibria, just switching to a pure strategy cannot be a beneficial thing, right, because Nash equilibria rules that out. Now, the question is, is it possible that I use, so in this rock paper scissor example, I said if I am playing 1/3 2/3 rock and paper, just by shifting to scissor, right, I do not get a better outcome than by playing rock and paper. Now, suppose I ask you, is it possible that by shifting, instead of playing rock and paper 1/3 and 2/3 of the time, I only play rock, okay. Then can I say something meaningful? Can I compare the payoff of playing rock versus playing scissor? The fact that X is a Nash equilibria and I am playing rock with non-zero probability gives me, allows, this needs an argument, okay, that my payoff for playing rock will be at least as much as the payoff for playing scissor.
The second definition, the action is also a distribution, right? Like the probability of
Yeah.
the action happening is
Yes,
1 and
one.
other is 0.
Yes.
So first definition implies the second definition, but I cannot see.
This is not a Nash equilibrium. That's what he was saying. See here, I have changed. I'm not talking about x is definitely x. If I were continuing to play xp, that would be at least be more than this. That's okay. But now I'm saying I'm not even playing xp. I'm just playing some other pure strategy. In this case, happens to be one where which I was playing with a non-zero value. Then I know the one that I was playing with non-zero value in x will give me at least as much payoff as playing a strategy that was not even playing an action which I was not even employing.
So for one player, I change the distribution to the action thing.
Yes.
The probability where that.
So the way to think about this is, I am as a player thinking, I am not just comparing my outcome while we are all at Nash equilibria. I am now thinking, what are the other action things that I could have done? There are two things. Either it's an action that I am already employing right now under X, which is a non-zero thing, or there are two categories of act. When I see XP, XP is my probability my mixed strategy, right? There are two types of action. An action which I am playing with some non-zero probability, and an action that I am playing with 0 probability. Correct? So now I am basically comparing what is my outcome when I choose a probable action which is of non-zero probability versus an action which is of 0 probability, while all others continue to play the same. It is very important. Okay? Then I see there is a good, basically it is like there is a reason why that was a Nash equilibria, because the actions I am playing there will give me at least as much value as the actions I am not playing. Okay? So why this is needs a bit of a proof. Okay, this is definition. I don't know why they wrote it as if and only if, but okay, this requires. So please try to do it on your own. Ask during Q&A. If you cannot, we will discuss it maybe later on. We'll have time during this thing. Okay, try to work out this properly.
Here we are not assuming that this prime P is in the support or anything.
Nothing. It's an arbitrary. So I was just saying. So suppose, okay, Vishwas, tell me, if S prime and SP both are in the support, what would this?
Equality.
Yes. That's what I was trying to say a while ago when mangled it completely. Yes. So that's the thing. If both of them are in support, it means they all individually give you the same value.
Because if something is less, you could just drop it from.
Yes. And that intuition is what we will use in the subsequent proof. So the idea is the following. If I have a deviating mixed strategy that gives me a strictly better outcome, okay, it's a probability distribution, let's say, but I look at it, I see the coordinates, right, I look at examine the values, I find the coordinate that gives me maximum payoff. I set all the other coordinates to 0 and dump my probability value mass 1 onto that, because that action gives me the maximum value anyway. So if there exists a mixed strategy, if there exists a deviating mixed strategy, then there also exists a pure deviating pure strategy.
So first thing implies second. Like the first property directly implies the second.
Which is your first property, that if there is a mixed strategy, okay, these are if and only if. Yes, if you have an action equilibrium, that is true. If you have a Nash equilibrium, this second condition is true. They are all if and only if. But wait, did you all understand what I just now said? And why, you may want to ask, why are we trying to find all these properties? It's like, do we just want to do a structural analysis in terms of properties of Nash equilibria and all? Yes, people do that, and that can be very revelatory. But here, the things that I am saying are basically to tell you that sometimes when some conditions are, some definition holds for a mixed strategy, being able to say something about the pure strategy can make the analysis easier, because if I am going to say that something is not a Nash equilibria, it means somebody has a deviating mix strategy, but that also means that the same person has an action that they can employ that will also be a it will give him a strictly better outcome. Therefore, I can actually now talk about that action instead of the probability distribution, and that oftentimes will make arguments easier. Okay? Any questions? So, maybe I write this here, this property. Given mixed strategy profile X, if, can you read my handwriting from the back? Is it readable? If player P has a deviation strategy, let us call it X prime P, then sorry. Okay. So, the deviation strategy means that is utility of P X minus P is strictly more than UP of this thing. So, this basically is saying, this just means that they are playing X. Okay. I think I need an eraser here maybe. This is what a deviation strategy means. Okay. That there is something he can do, this is also distribution by the way, that he can switch from xp to x prime p and he get a strictly better outcome than if what he was getting when he and along with everybody else were playing x. Then there exists an action such that UP SP exists action, let us say. Is this clear? This is why when you are in a situation where X is not a Nash equilibria, it is oftentimes sufficient to just argue about this pure the deviating pure strategy instead of wrangling with distribution. Okay? And there exists a very simple way of defining what this action is. You can identify what this action is. Can you tell me what? I said there exists, but this can be identified. So, which action will actually give you a strict improvement? If x prime p gave an improvement, yes?
Dominant.
Sorry?
Dominant strategy.
But why should a game always have a dominant strategy?
So like if it is with positive probability, like if it doesn't have a dominant strategy, if it has positive probability when chosen individually.
So, what is your definition? Are you using dominant strategy the way we defined earlier? Because that may not, dominant strategy is the way I understand it, and the textbook definition is, this is a strategy a player can play no matter what others are doing and always get at least as good an outcome as anything else, regardless of what all others are doing. A game need not have a dominant strategy.
So like weakly dominant, like not strong.
Even that need not exist. Where do you not have a dominant strategy? Rock, paper, scissors, battle of the sexes, etc., etc.
I can just trivially find it, right, by like brute forcing something.
Brute forcing, but what is it I am looking for?
Like all actions for that player.
Okay, SP is basically argmax of all the x. I look at this successful deviation, within that I look at all action where this is small sp. Okay. This is why I had written S to A. I myself, after some point, I myself will not be able to understand what is this thing. SP. Yes, let me write here this. I see this successful, this deviation strategy. I examine each of its coordinates, right. The coordinates are only this, because these are the actions available to this player P. I pick up the one, right, this thing, sorry, such that you, this thing, what is it? UP, how do I write this? I want to say the UPA, yeah. I don't need x. Why do you say x minus?
Because I want to find the maximum over all the.
Okay. So the fact that this, okay, I am looking. What am I saying? I am saying I want to see the probability done. I am basically going to look at the action, the yes UPA, such that x prime P A is more than 0. I look at the support of the x prime P vector. I see the support, this is the thing. I see among those who is the one which gets the maximum utility.
Yeah, but utility is defined for all players together. Yeah. So no product.
Okay, sorry, yes, that's why, correct, you are right. Sorry, yes. A and x minus P, yes, correct. Okay. So this is how you can define SP, and there can be multiple such actions, but all of this thing, whatever this is, it will be true. That is why we say argmax, okay. There can be multiple this thing, but that, okay. So this is why this is very helpful. We will see how we use this, that when we say there is a deviation strategy, it is enough to argue against pure deviations, okay. All right. So now let us just go back a little bit and just see quickly. In prisoner's dilemma, what kind of a Nash equilibria do we have? Do we have pure? What? Sorry? Louder? Both confess. Okay, is that the only Nash equilibria? No. What about both remaining silent?
But the deviation
One
there
can just
can
confess and like reduce his payoff rate. So
Okay. So if I take in silent, and what happens? This, who switches? This guy is switches to confess, then he gets a better payoff. Yeah, this is like the number of years, or yeah, this is like the cost. Yes. Okay. So this is not a Nash equilibrium. What about this? Are these? Does this constitute a pure Nash equilibrium? Silent, confess.
then if he confesses, then he gets to the fourth. Like,
This person who is silent, right? If he confesses, right? From silent here, you can only go here, right? From silent confess, you can both of them. Yeah. So there is an improvement path for him also. So this the thing that we saw was a dominant strategy. It's also a Nash equilibrium. Okay. But dominant strategies need not always exist, because as we saw before, that it's not does not exist in most games. So this is a pure Nash equilibrium. Like, there is literally a pair of actions that these people can do, which will be give them the best possible payoff.
So what is the dominant strategy?
Okay. So the dominant strategy is a strategy that you can play irrespective of what all others are doing, in the sense that it will give you at least as much payoff when you are playing that strategy versus anything else other people do. So in Nash equilibrium, we don't allow others to do anything, right? Others continue to do what they were doing before, and you are the only one deviating. So dominant strategy, the dominant strategy equilibria, when they do exist, is a much stronger form of equilibria. Okay. All right. So now we have already talked about it. rock paper scissors doesn't have a pure Nash equilibria, but it has a mixed Nash equilibria, literally that 1/3, 1/3, 1/3. Yes.
The prisoner's dilemma, if both are confessing,
Yeah.
then none of them has the deviation strategy, right? If
Yes. Yes.
So because none of them have a deviation strategy, it's a Nash.
Yes.
That's the definition.
That is a yes. Yes. None of them have any deviations. Right. That is why it's a Nash equilibrium. Okay.
So could you give an intuition of why this is correct using rock paper scissors? Like it can be any mixed strategy profile, right? The X. Suppose I say 50%, 25-25 as rock paper scissors, and yeah, and there is some deviation strategy that improves my this thing, and suppose that is 1/3, 1/3, like.
Okay.
Because we know that will give me 0. So now which is the one? What is the action that will maximize it?
So this is the strategy that I was initially playing,
Yes.
and then
This dominates the previous one.
yes. So notice something, that this is why this was important. Like if this is a better strategy,
Yes.
I mean that means this is not a Nash equilibrium. So this is a better deviation strategy. Let's look at x prime p by our notation, right? Okay. So from here, if I look at that payoff matrix, I basically have to see that okay, all three of them are basically in the support.
Yes.
So in this case, each of them you could just move to just anything 1, 0, 0. They are all equivalently good actions.
So you're saying they are better than XP?
Yes, they will give, if xp was not a Nash equilibria, x prime p was giving him a strictly better outcome, right?
Yeah.
We will see that playing any one of these pure strategies, this is why I made this into a set element, this thing. There can be there can be multiple better actions you can play that will give you a strictly better outcome than what you were playing, than what you were getting under X. So this is that case.
So you have not proved this, right? I mean, this requires.
Yeah, you guys, how much am I doing time wise? I need to get to the proof of Nash equilibrium. Try to work these things out in the class, okay? This is what I want the Q&As to be. Get your hands dirty with working out some simple games, that's it. 15 minutes, okay, I have to rush, okay? All right. Yes, because this is the star of the show. Okay. Okay, Vishwa, that's a very good question. So work out, use this Nash, use this payoff matrix. There was a mistake here. This is -1 + 1, okay? And work out among that thing what would be a better strategy than this. Okay. Wait a minute. That's probably not good. This was half here, right? So okay. So definitely. Sorry.
The other player is playing, let's say.
Yeah. Yes. Actually, that depends. Yeah. So it's not correct exactly. So I kind of have to take into consideration what the other player. So it's suppose there are two people. So what XQ strategy is, right? That needs to be, take an example of this. Maybe what XQ plays 1/3, 1/3.
Yes. Only then.
But then this can't possibly have a deviation. Yeah. This. Yeah. Okay. Okay. Okay.
We should first take a set of two tuples, right?
Sorry?
Yeah, that
We
is.
should take a set of two tuples, x, y, x, y, x, y.
No. This is
For the mixed strategy.
mixed strategy. X consists of XP and XQ.
Yes.
XP is a distribution on 3 actions, rock, paper, scissor. XQ is also a distribution on 3 actions. This is why this is a 3-size vector. So this X vector itself is a 2-size vector, but each one is a vector of this thing. Okay. Yeah. So work this out. One of them will be actually this thing. It actually depends on what. So this one says, okay, I have to do this. We'll come back maybe after I finish the proof of Nash's theorem. Okay. So work out these things, okay? What kind of Nash equilibria they have and so on. Now the question is, you may want to ask, why would they even need to have a Nash equilibria? We know this for a fact because of this. sort of seminal result by John Nash. He published it. Was really tiny paper, almost the journal size is like this much, 2.5 pages, and he showed that any finite game always has a mixed strategy Nash equilibrium. Okay, it's not that it has a pure strategy equilibrium, because clearly rock paper scissors doesn't have one, but it always has a mixed strategy Nash equilibrium. So now the question is, what's a finite game? Finite games are all sort of games that we have seen so far, at least the specific examples. Finite games are those where the number of players is a finite set and the actions available to the player is also finite. Okay? Any game that does not match both of these specifications is called an infinite game. Now you may want to ask yourself, what is special about infinite games? Why are they excluded from Nash equilibrium consideration? Okay? And for that, there is a very simple example where this is a situation where you cannot have a Nash equilibrium. You can argue it. It's easier to argue that you don't have any deviating action. It's slightly more harder to argue that it does not have any deviating mixed strategy also. But from there we know that if there was a successful deviating mixed strategy, there should also be an action, deviating action that would give me a better payoff. Okay? All right. So this is something that Sanjay wishes to do during the Q&A. So you guys think why this setup, where every buyer basically has budget 1, he wants to buy some item, buyer A can only buy from this guy, buyer C can buy only from the seller 2, but buyer B has this choice of 2 sellers. He obviously is going to try to buy from the person who will give him the product cheapest. Okay? Now these sellers have this thing that they can't do price discrimination. Like if he's selling a product to buyer C at a certain price, he has to sell the same product to buyer B at the same price. Now the question is, what kind of price should the sellers ask so that they get the best possible payoff? Which I'll say, I mean, it's the most classical payoff. It literally, the word payoff is like you want to get maximum money out of selling something. Now if you exorbitantly price something, buyers who have options to go to see other sellers will basically leave you. So you kind of have to be competitive. But if you drop your price too much, right, then you again get a very low payoff. So this is the sort of a thing. Okay? So now the strategy here is this price is what you are quoting your price is the seller strategy. This is clearly an infinite possibility space. The number of players are finite, but the action space is infinite. Okay? So here you don't have a Nash equilibrium. Okay.
Does Nash theorem put some kind of restrictions on payoff function?
Nothing.
So utility function can be anything.
Okay? It can be negative valued also and so on and so forth. Nothing. Just the size of the player space and their action space. Okay? All right. So any finite game has a Nash equilibrium of mixed strategies. So let's say for a mixed strategy X and a player P and an action available to that player P, I will define this quantity called gain with respect to P, the player P, right, for every individual player P and for every individual action SP with respect to X, I define this quantity. Tell me quickly, what does this quantity represent?
The gain you get by deviating.
To this action SP, right? So if your gain is negative, meaning you are losing, then basically you take 0. Gain is 0, right? You don't have a successful deviation. Otherwise, this gain function will pick up this thing, correct? So to show that any sort of generic arbitrary finite game has a Nash equilibrium, what would it be enough to show?
That gain is positive.
Gain is positive. That means it is not a Nash equilibrium. 0 for? No, I am trying to show that for a vector x, right? Okay, so I am saying for a vector x, this quantity is defined. Vector x means it's a mixed strategy profile vector, right? You can define this quantity. To show that the game has a Nash equilibria, what will I have to show?
It's all the same.
Gain is 0 for all players.
For all
One by one, it's important. You want to say something?
The gain is 0 for all players simultaneously for a particular action.
For a particular action. But you see, the Nash equilibria is a strategy profile. We have to show that there exists such an x such that gain P SP of x for all players and for all action is 0. Correct? We are showing the existence of a Nash equilibrium, right? A Nash equilibrium is basically a specification of a strategy profile. So, given that we already know this, if there exists, if a particular profile, a given x, is not a Nash equilibria, there exists a deviating pure strategy, right? And for that x, this value will be positive. So, if I can show that there exists x for which no matter which player you take and no matter which action you take, the gain is always 0, that means x is a Nash equilibrium. Yes, small s. Yes, small sp over capital sp, yes. No, sorry. Sorry, this is very bad notation. This should be small sp. I'm sorry. I have to write it somewhere. Where should I write? I'm sorry. This is all my. So, small sp is an action in the action space of player P. Gain is defined with respect to this mixed strategy profile x with respect to this player and this action SP. This is max. What is the benefit this player gets P by deviating to this action while all others remain the same? If he gets no gain, it will be 0, otherwise it will pick up this value. Okay? So, you agree that to show that there exists a Nash equilibria, I have to show that there exists such a vector x such that for all players P and for all possible actions available, the gain value defined like that should be 0.
So this would only show that there exists a mixed strategy which is better than all pure strategy, but it doesn't show the mixed strategy is better than other mixed strategies.
So, if there exists, take an x which is a mixed strategy profile. If this is not a mixed, if it's not a Nash equilibria, there exists some deviating strategy for some player,
We are using.
right? Correct? It's okay, Vishwa, these are important questions, right? So, I define this x prime as this guy switching to this mixed strategy and all others continuing to play this. By this sufficiency condition, there also exists some action SP, right, such that you basically don't define x double prime like this, S prime would also be a successful deviation. Okay? Therefore, my gain function is defined only on actions, right, not pure strategy. Gain for this will be SP small p p x double p greater than 0, correct? This x will be greater than 0, right, because literally I will be able to detect this s prime small s prime p, this thing. Okay. So, this is where the entire proof will now be, showing that this such a thing exists. So, how do we do this? I mean, the simplicity of the argument is like, it's remarkable how simple the ideas are, but how beautifully they sort of work out. Okay. So, for any mixed strategy x, take any x of this, and for a player P, we will define this hypothetical, this sort of a new function y, okay, where I am defining yp is a new mixed strategy for the player P, where he plays this action SP with this probability. So, it is a perturbed version of the original strategy that the player P was playing. Player P was originally playing XP, mixed strategy, right. So, he was playing probability, whatever this quantity is, XP, SP is a probability mass for the player P playing the action SP. Now, for the same action SP in this new probability, new mixed strategy, what are we doing? I am perturbing this by this gain value. Gain when applied to x for this particular player for this particular action SP, and I am normalizing it by this quantity 1 plus summation of all the gain quantities for this player P. So, this summation is for over the entire action space of this player P. I claim that when I look at the vector yp, which is just the same thing as we were doing before, yp is basically a yp action 1, yp action 2 and so on and so forth. So, to prove that this is a mixed strategy, yp constitutes a mixed strategy, what do I need to show? This is some thing I defined, right, some perturbed version of xp. What do I have to show this is actually a valid mixed strategy? Somebody? 1, exactly, right. This is a valid distribution. So, summation of all these yp sp values is 1. So, now when I do that addition, you see the denominator for each of these terms are the same, and this summation gets added here xp sp, right, the gain this thing. If you adjust it, you will basically summation of, because xp itself is a distribution, summation of xp sp would be 1 and this quantity summation will be exactly this. So, yp is actually a valid distribution, and therefore, it is also a mixed strategy, it represents a mixed strategy for player P. Now, I am going to claim, and of course, we do this for each player P. Okay. So, now I am going to take the function f that is defined from the distribution profiles, the mixed strategy profile space to the mixed strategy profile space, and I will say you give me a mixed strategy profile x, I will give you y. This is the function. Okay. So, literally you gave me an x, whatever x you give, I will give you a y using this description. Is it clear? So, we are still trying to argue, just to recap, that there exists such an x, such that for all player P and for all action SP, the gain is 0, right. In search of such an x, I basically created a perturbed y for each such potential x. Imagine you are able to look through the entire distribution space. For every x, there is a y. Okay. Now, for a function such as this, I am just going to claim, and I am not going to prove this, f defined like this is a continuous function. If it is not a hard this thing, but you need to use some definition, continuity and so on. F is a continuous function. This domain delta, as defined before, okay, has this property called compact. It is convex, sort of it is this thing, yeah, it is convex and compact. Okay. Therefore, yeah, this result, this sort of thing, I thought it was here. Okay, this sort of a result is called a fixed point theorem. Lots of people have, mathematicians throughout the ages have proven fixed point theorem based on different conditions. Brewer's fixed point theorem is remarkably complete in the sense that if you drop any of these conditions, you do no longer get a fixed point. It says that whenever you have a space D of the Euclidean space such that it is both convex and compact, then any continuous function will have a fixed point, meaning you pass that point to f, you will get x back. Okay? So, the original proof of Nash did not use Brewer's fixed point theorem, he used Kakutani, that is a different sort of fixed point theorem with slightly different rules and so on, slightly different hypothesis, but then later on in a very short while he realized okay, Brewer's works just as well and it is more sort of tighter. Okay? So, that is the thing. So, all these conditions that are required to apply Brewer's holds for our construction. Delta, you just have to take on faith that delta is a convex and compact this thing, it is a product space of simplices, simplices are convex, compact, so product blah blah blah, it is a topology analysis and so on. So, just have to accept it. This you can show that f is continuous and therefore, this function f has a fixed point. Okay. So, we talked about Nash equilibria and we defined a function f which sort of is a perturbed version of this thing, it kind of is still artificial looking and now we are talking about fixed point of f, right. So, the natural question is how are they related? I mean they are part of a proof, so they have to be related. So, the most obvious sort of hint is that this fixed point itself is a Nash equilibria. Okay. Is the proof so far clear? All we did is define a few things, right, that gain function. From there we defined a perturbed mixed strategy. For any mixed strategy I defined a new mixed strategy. That definition allows me to use Brewer's to claim that that function that maps that given mixed strategy to this perturbed version actually has a fixed point, right. So, now how does this fixed point relate to my Nash equilibria?
For all players here, for all actions any player can take, the gain will be 0.
Yes, basically that is the point. You look at x, x1, x2, xp and so on, xn, and you have y, and after you map f to y, you get the same vector of xi's back. But these xi's were obtained by doing the gain function. The denominator is always the same for all of them, but the numerator 1 plus that gain value, right. So, you started with this thing and you get this exact same thing at the back. So, it must, so yeah, so that it requires a proof, but that is basically the idea, that the perturbation basically brought you back to the same point. So, it must be that the gain is 0. Okay. So, okay, so I guess, yeah. So, f, this is the layout is a bit weird. Okay. So, the lemma everything wraps up after this is that the fixed point x is a Nash equilibrium. Okay. Why is it sufficient to show that gain p is equal to 0, that for this fixed point, this is not a Nash equilibria this thing, for the fixed point x, gain if this is equal to 0, why is this sufficient to show? So, it is basically the other way round of what she was saying.
If the gain is 0, then there is no deviation strategy, like they won't deviate, players won't deviate.
Yes, gain being 0 will itself mean, but what does that have to do, for example, but see the point was that we talked about as long as we could find any point x in the mixed strategy profile, if there was a, if this had the property that for all players p and all actions p, sp, the gain was 0, that itself would be a Nash equilibrium, correct? Now the question is, how do I find such a Nash equilibrium? Now what we are saying is that for the fixed point x, so Nash equilibrium implies that gain equal to is 0 for this strategy, and if for any x the gain is 0, then that is also a Nash equilibrium. That is an if and only if condition. So, if I am going to claim that x is this fixed point x itself is a Nash equilibrium, it should be sufficient to show that the gain for this thing is actually 0, correct? Because the definition of the gain was with respect to the original x. It has nothing to do with fixed point as such, but we inherit that property that the sufficiency of x, of this particular fixed point x, to be a Nash equilibria is basically given by the fact that the gain should be 0. Okay? So, now that is all we will see, that suppose now this fixed point x has a player and has a strategy, has an action SP for gain is greater than 0, then what happens? Yes. So, let us write it, I do not know how much I wrote it here. Okay. So, Yp, this is just by definition, right? Yp was defined this, because x is a fixed point, Yp_Sp is actually equal to Xp_Sp, correct? That is what fixed point would mean, Yp_Sp is equal to Xp_Sp. Now, if Xp_Sp is greater than 0, this term in the numerator is greater than 0, correct? And you have this plus something here. In the denominator, what can we say about the denominator? Sorry?
It's always greater than 1.
Yes. Correct? Because whatever xp, whatever you have here, gain p_sp(x), which is greater than 0, right? We have assumed that. That is making this, that quantity also appears in the summation, in the denominator. So, the denominator can never be just 1, it has to be 1 plus something, correct? Now what? Why is Xp_Sp 0? Why is Xp_Sp 0? Why is it greater than 0? We just made some observation about the gain and the denominator of this. What?
Because if it's 0, then Yp_Sp cannot be 0, and we are assuming that it's a fixed point.
Not Yp_Sp is not 0. Yp_Sp is actually equal to Xp_Sp.
Yeah. So it cannot be 0. Yp_Sp.
Gain would be negative.
I am going to just write this as this thing, okay. So, this quantity is greater than 0 by our assumption, correct. This makes this denominator to be greater than 1, right. Now, Yp_Sp should be equal to Xp_Sp, right. Xp_Sp is already sitting here, you just have an Xp_Sp here. For this to be actually this, if this is greater than 0, right, and this is the denominator, if this were to be, if this were, because this is greater than 0, the denominator automatically becomes more than 1, right. So, you can't get Xp_Sp back on the right hand side, and therefore, you can't get Xp_Sp to be equal to, I need this follows, right. Yp_Sp can't be more than Xp_Sp, it has to be equal, and the denominator is not 1, and the numerator here has Xp_Sp plus some positive quantity. Clearly, that cannot be true, right. So, what should happen?
We can argue that if Xp_Sp is 0, then gain has to be, the gain P_Sp should be 0, but that contradicts the fact that gain is greater than 0.
Yes. So, no, but up until here, what did we assume? We just said, okay, gain P, if this were actually equal to 0, we are done, right. So, we are saying suppose this is equal, this is greater than 0. If that is greater than 0, this numerator, whatever XP is, whatever this may be 0, not 0, doesn't matter. I am trying to prove this, right. Whatever this is, the numerator has already become something greater than 0 because this quantity is greater than 0, correct. And the denominator is not 1, correct. So, how can this whole thing now be equal to XP regardless of whatever it is, whether it is 0 or not. Suppose okay, let us say suppose XP is actually 0, correct. So, this one disappears and you need all this quantity to be 0 then, right. This quantity is 0, you need gain P x divided by this thing to be actually equal to XP which is 0 by definition. That cannot happen. So, therefore, XP is not 0, okay, all right, fine. So, now what was okay, so XP is not 0, then what? What should we do with it?
Then we can just cross multiply.
Cross multiply and do what?
Like we have XP on one side, we can multiply it with 1 plus summation gain.
Okay, and then I am trying to prove that this, I just need to prove this, okay. So, just tell me how from this thing I get to this. That ultimately I need to show gain is 0.
You will get something like XP plus XP into summation gain equal to summation gain.
Okay.
Plus XP, yeah. And then it will imply that the summation gain thing is 0, which is only possible when the gains are 0.
Okay. So, I think, okay. So, now I am going to show, okay. So, let us just keep this, okay. So, I do not see how your name I forgot, I do not see how you would get an argument like this, but this is a simpler argument. All we know is XP is greater than 0, okay. Now, I deleted the definition of YP, I needed it. Notice something, we will again work with the definition of fixed point, okay. So, YP XP is equal to the definition of YP which is XP plus gain P x 1 plus this normalization, this thing prime P okay. This I have, are there no color? This is saying XP is greater than 0. Okay. Fine, this is XP is greater than 0. Then what can I say? If XP is greater than 0, given that I claim there exists a action for this player such that he basically gain will always be 0, I want to write it this way, UP, if this guy switches to something, this thing, he actually gets less than what he was getting before. If there exists a strategy SP for which XP is more than 0, there should be a strategy S prime P for which the deviation is of the opposite kind, like he loses value. Why do you think this is true? Okay, I should also write here XP S prime P is in the support, this is important, yeah. Why do you think this is true? Yes. So, I go back to my utility function definition of this. This is the definition, right? The payoff from x, right? I write it this way. There, think about that term, that strategy SP. That is a term in this equation, in this summation, that XP SP is greater than 0, and this quantity UP SP x minus p is of greater value than this whole thing UPX. So, you have a term here that makes this quantity, this side, more than the left hand side. There must be another term that brings that back, right? Existence of XP SP, which is positive, and the fact that this quantity UPSP x minus p is greater than UPX, right, says that for this equality to hold, there must be a term in the summation that brings that value back. So, they can left hand side has to be equal to right hand side. Okay. So, that is the reason why we have such a S prime p, this thing, such that this is less. Okay. So, now what do we do? Now, what is next? Suppose we have this. Okay. Now, can we say something about the gain? Again, we have to go back to gain. Gain has to be shown to be 0, right? So, what is that gain? Well, use this thing, right? I will define this to be this, right? You define that there is, yeah. So, for this, my notation, this is the same thing as this, okay? Yeah, okay? I am talking about this thing, same. That action which gave you a lower payoff will be the one where gain should be 0, because gain is literally capped at 0, right? You can't fall below 0. So, that is it. The fact that we kept on arguing the fixed point was an important thing that allowed us to say that XPSP, even after perturbation, I actually do not get a different value, right? When that is the case, then one or two things can happen. For this value x, right, I look at each term, each action, either that is a positive value action, right, it is in the support, this XPSP, if it is equal to 0, right, then I get a contradiction. So, I know that this has to be at least greater than 0. But if this is greater than 0, the fact that this is the payoff, expected payoff for the player P for x tells me that this the summations here need to basically balance each other. If there is a term here that makes it larger than this, meaning if the gain is positive, right, there has to be an action, there has to be a action that brings the value down. Otherwise, this can't be the expectation. So, this is sort of an argument, is fairly standard if you know, like in certain type of analysis. Okay. So, it may seem all magical and all. When he came up with it, I do not think this was that, I mean, yeah, this is early 1920s, 1940s and all. But now fairly, like people who work with these sorts of arguments, they do it, like, you know. He said expectation was a definition of expectation, you have to have the something has to counterbalance this thing, okay? And once you get this, you know the gain has to be 0, okay? So, we have shown that there exists a Nash equilibrium, gain P S double prime P x is equal to 0. Okay. Now, okay, but are we done? I mean, we are almost done, but there is still something to be left, because the Nash equilibrium definition tells us to say that for any player there exists no strategy, like rather every action will give you 0 gain. We just showed this for one possible action S double prime P, It says nothing about all the other actions. Agreed? Right, the definition of Nash equilibrium requires us to say gain is 0 for all possible actions. This is just saying here is one action for which it is 0. Okay, so now, yes. So, what went wrong? Then x must not be a fixed point. Why? If there is even one point here for one action which is, because if I substitute this quantity here, right, this quantity becomes 0 as we have said here. You have something xp s double prime p which is greater than 0 by this, we know that is property this thing. So, you have something here which is greater than 0 plus a 0 quantity divided by 1 plus, what do you have, what can we say about this summation? It is still greater than 0, why?
Because S dash P was
Yes. So, this whole thing left hand right hand side cannot be equal to left hand side. Okay. Okay. So, it is not fixed point. So, it contradicts what we started with at the beginning, which is that x is by definition x was a fixed point. Okay. So, I think no course on algorithmic game theory should be complete without talking about proof of Nash equilibrium, because there is so much work on game theory happened because of this definition and how. So, let's just observe a few things. Okay, maybe it's not an observation; it's just a fact that you have to accept that this is not a constructive definition. It means there exists a fixed point. And there is no, in general cases, there is really no efficient algorithm of finding a fixed point. That is a huge area of work, like under the what are the restrictions under which we can always find a fixed point and so on and so forth, okay? And what kind of algorithms we can expect to have and so on. So, finding, other than doing an exhaustive search, of course, you could do an exhaustive search and so on. So, okay, just 2 more minutes, okay? So, this is not constructive. Therefore, using this, any proof just means there exists a Nash equilibrium. We do not necessarily know how to find it. Okay? All right. Now, there was something else. So, the definition, okay, the definition of Nash equilibrium is something that, okay, if we can't find it, players are playing independently, they are competing against each other, what is the hope that the game will ever attain a Nash equilibrium, right? That is a natural question. We have this nice solution concept called Nash equilibrium, which seems to be sort of robust in the sense that if people somehow magically by some reason or another are at that, if everybody is sort of playing that sort of profile where this is a Nash equilibrium, there is no reason why anybody individually will do something different. So, that is the goodness of the definition of Nash equilibrium. Why a game may or may not attain a Nash equilibrium, that is a different question. Or when analyzing a game, how we find such a strategy profile which is a Nash equilibrium, that is also a separate question. Okay? So, I leave you with this, that we just saw that there exists a Nash equilibrium in all finite games, and in general, while we cannot find it under some restrictions, one can, and we will see one such thing in the second part of the after the lunch.